This example will show using RAP for radio communication coverage and for radar coverage. There will be examples with jamming and without jamming. We will start without jam or radio communication. I place stations here for radio communication. I'm making use of the prepared templates of RAP, which is a convenient way of quickly creating stations. This will be an analog base station operating on 68 megahertz. It's a 40 watt radiated power transmitter and 24 meter high antenna. I make a copy of this by using the left mouse button, pressing it and the control key at the same time, and now I have two stations there. Let's change the name to base 2 and move it a little further away. Let's place it there. I will put these into a network because stations in a network do not interfere with each other, and in this case that's what we will be interested in. Stations, our wanted stations, do not create interference. It is just the jammer that I'm going to place here that will give interference. Now I run calculation. We will run it as two individual single station calculations with an analog mobile, and this is without jammer, so I gave that as a description of the result. And it calculates. Now it's ready. The presentation will be color coded with red indicating better than 10 dB signal to interference ratio. Green will be better than 22. Since there is no interference in this calculation, the interference really is receiver noise. So the signal to noise ratio is what's going to be displayed. That's the coverage of base 1, and that is base 2. I'll take away the color of the map because it tends to obscure the presentation when we have colors in the result. Like that, okay, and hide the results again. Now I'm going to place a jammer somewhere. I'll place it here down south somewhere. Making use of the template again. I take this jammer, put it on 68 megahertz. This jammer has a radiated power of 1 kilowatt compared to the 40 watts of the transmitters. And the antenna is about the same as the base antennas. So there is the jammer. Now let's do the calculation again of the signal to interference, and now it is with jamming, with jammer like that, and we'll calculate again around each station. It takes a little longer to calculate now since it is one more station to calculate for. The jamming signal is calculated also. And make the presentation. The coverage is much smaller now, which is obvious. And it is typical that we have this unsymmetrical appearance of the ridge since we are calculating receiving in the mobile, in the 2-meter high mobile antenna. And when it is far away from the jammer, it will have less signal from the jammer and comparatively more signal from the base. And when it comes to the jammer, it is the reverse. So showing both at the same time, it is quite evident that the range reduction is severe through this jammer. Okay, that was communication jamming. Now I delete these stations and I hide the results. And we will instead go to the coast and place a radar station on an island here. So I will place it on this island. I'll zoom in to be able to place it accurately on that island. Yeah, we will have it. Place it here, a new station and TX position, and select a template. This is a coastal surveillance radar, a modern radar operating on 9.375 gigahertz, 18-meter high antenna above ground level, and 80.6 watt pulse power. So it's a reasonably high power radar. First, I'll calculate without a jammer, and use a target height of 20 meter above sea level. It's probably sufficient to calculate the 40-kilometer radius here. So I'll call it radar without jammer and press OK. The radar on this island, I'll go back to the previous scale because the coverage of the radar will be more suitable to display in this map scale. It is soon ready, and what the type of calculation I did now was to present the visible sizes of radar targets. It's the default setting: 1 square meter, 10 square meter, and 100 square meter. 1 square meter represents a very small boat, and 100 meter a medium-sized fishing vessel. Okay, and let's display the result. It looks like this. Red again was the 1 square meter, and yellow was 10 and 100 square meter. It's typical that the radio optical horizon is somewhere around here, so it's not feasible to get a very much larger range. Let's see what range we got. 36 kilometer or so. Okay, now let's put a jammer somewhere. I place it here, new station and TX position again, and go for a jammer. Put it on 9375 megahertz again. Again, meaning on the same frequency as the radar. This is a 40 dB watt, 10 kilowatt pulse jammer, 10 kilowatt jammer, and 25 meter high antenna height. Making exactly the same calculation, only this time setting the jammer. So I set the jammer. Here I can introduce a requirement for interference margin. It's set to 0 dB, but we probably need some interference margin for good detection. So let's say dB or something. This is with jammer and calculate. The coverage display here indicates that we have C reflections due to the geometry of the path, because we do not get a homogeneous result. We can see some. We need to have a larger target here to see it, so it's a gap in the coverage for the small target, and so on. RAP has a very good help function, and talking about that while calculation is going, pressing the tool there, it goes automatically to the active tool. The radar coverage has the radio optical visibility, the free space coverage, and the transmission loss tabs, and it's possible to click in a help file to read more about what these calculation modes mean and what they do. I close the help function again, and we'll wait for it to be ready. So the radio optical visibility includes consideration to the terrain features, and in order to present the maximum visibility. This does not then include the radar equation or the link budget of the radar. Okay, it is ready. So let's show that. And here it is evident that the jammer has an impact in the direction of the jammer. The radar is almost blinded, which is quite natural that would be the case. And there is some effect to the visibility of the radar size is also a little beyond this very narrow beam. This blind sector, or blind, the width of this is basically directly related to the beam width of the radar antenna, naturally. When the radar beams away from the jammer, it attenuates the jammer a lot, so it will not be so much affected. There is one more function that is of a high interest for using RAP for electronic warfare applications. And I move the map now because I'm going to start the cost and coverage optimizer tool. I have loaded a settings file to it, and the settings file was this one, coverage optimization jamming in Motala. And it has defined to produce jamming in the area that now is shown in the map. That is the desired coverage area for the jammers. The allowed placement area for the jammers is here. And in the evaluation tab, we can see that the requirement for the jamming success is produce at least 30 dB, the received power at least 30 dB higher than the sensitivity limit of the receiver that is going to be jammed. And the receiver that is going to be jammed is a mobile, it's a RAP base station. It's actually the same type that we used for the coverage calculation, the 24-meter high base. So the jammers are going to produce at least 30 dB higher than sensitivity of the base station over at least 95% of the jammed area. It's possible to set a limit on the number of resources. In this case, if I run it like this, it assumes that we have only 2 jammers at our disposal, and the response by the program will be where to place the jammers in order to have greatest effect to achieve the 95% covered jammer area. If I do not check it, it comes up with the number of jammers and their locations that will be required to achieve this jamming success. I will not run that, but it was relevant to talk about it since this presentation is for a military application of and we have shown radio communication coverage and radar coverage, and in both cases with and without jamming. So that completes this presentation.